So welcome back everyone for this session of the Cardiff Analysis Seminar. Today we're delighted to have Markus Waurick from Freiberg, and he will talk about maximal regularity for evolutionary equations. So Markus, the floor is yours.
Thank you very much, and thank you also very much for the invitation. And apparently it has shown quite some attention. So 24 participants from all over the world. I'm quite excited. And today I'm going to talk about maximal regularity for evolutionary equations. And this is based on a joint work with Sascha Trostorff from Kiel. And for those who are interested in more details of the story, they can look up the archive reference I put up. My talk is roughly being separated in three motivation and history. So 3 sections. The first one will be what will be the main story, the main subject we are studying. The second will announce the main theorem, and maybe I throw some ideas in on how to prove this. And in the second part, I will maybe provide some applications, or rather position the history of the problem into the setting we are discussing here. So first of all, the 0th part will be about the famous Lyon's problem. And I'm saying famous because many people know, but of course not everybody. So I'm not expecting any one of you to know. So I recall this briefly. So let's take a number t greater than 0 and a non-autonomous form. So this is a mapping from the time interval 0 to t times v, and v is a Hilbert space. And what should be the properties of the non-autonomous form? Well, it should be measurable if you put in vectors from v. It should be bounded uniformly in T. As a bilinear form. It should be bilinear in the second 2 arguments, and it should also be positive, or the real part should be positive in the following sense, that we find some alpha uniformly in T and V such that we have this estimate. So all T, V, and W, and some alpha bigger 0. Okay, and this setting already, this defines an operator, calligraphic A of t, which is a bounded linear operator from V to V prime. And the setting of this operator is, if you apply this to some V, it should be the functional where you let vary the last argument of your form. And in order to formulate Lyon's problem, I still need another notion, which is the MR space of V and V prime, which is the maximal regularity space. In this case here, the intersection of H1 with values in V prime intersected with L2 of 0t with values in V. And then it is well known that for all f in L2 with values in V prime, there exists a unique U in this MR space with the property that U prime of T plus calligraphic A of T applied to U of T equals F of T for almost every T. And I assume the initial value 0 at 0. And I call this star. Okay, so this is all well known and not a problem in itself so far. But if I want to know something more from this regularity here, so see, you have a sum of operators on the left-hand side. So you apply the time derivative to U and this calligraphic A of T to U. But you could also realize that you could also consider a different operator realization of calligraphic A. That is, if you have, if you are in a situation that you have a Hilbert space H, which where the Hilbert space V embeds densely into, and then by usual Gelfand triple construction, you also have that H embeds into V prime. So if you ask something more of the right-hand side F, say if this F was not in L2 of 0T but values in V prime, but a little bit more regular, namely in L2 with values in H. And then you can ask if you consider the operator realization of your form in H and not as this bounded linear operator from V to V prime, you can ask whether U is actually in this domain of the operator realization. And if you want to put this into a definition, the definition is as follows. We say that the form A satisfies maximal regularity if for all F in L2 from 0T with values in H now. So this is the important bit. The solution U of our problem above satisfies U actually is in H1 of 0T, but now not in values with values in V prime as it is assumed above, but now I shall hope for U to be to take values in H. And if this is the case, then you see that, so maybe this is a side remark. Then U prime of T plus calligraphic A of T, U of T equals F of T is an honest equation in H. And moreover, if you write this as an operator equation as operators from L2, 0T with values in H, you could also write that D and this is the operator realization in H, applied to U equals F. Then you could also say that this U is in the domain of the intersection of those two unbounded operators in L2 of 0t with values in H. And this is the maximal regularity you could expect for you to have if you consider this equation in L2 of 0th, because your right-hand side is in L2 0th, and the derivative applied to U is then in L2 0th, and also this guy is. And since your right-hand side is already in this L2 with values in H space, it suffices to assume from one of the applications to stay in the space L2 0th to have it for the other. Okay, so this is maximal regularity, and Lyon's problem now is characterize all non-autonomous forms A which satisfy maximal regularity. And this problem dates back to Lyon's in the 1960s, and has then been dealt with by many people. And it's also you would what conditions could you think A could have? Maybe A is just as is, and you hope for maximum regularity to be satisfied by such an A, or you would assume some regularity conditions in T. And in fact, if you assume that A is in C1, for every vector V and W you put into this, so weakly in C1 if you want, then you can show that A is satisfies maximum regularity, and this goes already back to Lyon's. But I want to have a more recent look into this problem class. So latest results. The first one I'm going to present is the one of Dier and Sascha, and I will abbreviate this since I will talk about this some more later on. D and Z, and this is from the year 2016. And it shows that if there exists a delta greater 0 such that the integral over 0t of A of t, calligraphic A of t, calligraphic A of s squared, and this is in the V to V prime norm, over t minus s to the power of 2 plus 2 delta ds dt. If this is finite, then A satisfies max reg. And you could phrase this also as a regularity condition, and this roughly says that, or this says that your that your form is in a fractional Sobolev space, and a different, somewhat related result is the following. If you look into a result of Osha and egot, this is from the year 2016 as well. There they say, well, if you restrict yourself to divergence form operators like this, and you assume homogeneous Dirichlet or Neumann boundary conditions, and you assume that the supremum over all subintervals of 0 to t of 1 over the interval of the expression ATX minus ATY. So these are basically the coefficient functions of your non-autonomous form. Raise this to the power of 2, divide this by t minus s squared ds dt. And if you ask this to be finite, then your form A satisfies maximal regularity. And so in a way you got rid of the delta.
Sorry, Marcus. So it's for all x and y.
Yes. Yeah. So the supremums also. So this is for all x and y in well, Rn.
Something strange there. There's t and t in the numerator.
Oh, yeah. This is strange.
Yeah. Yes.
Thank you. Okay, so this is the so you have the coefficient is a of t, and then this can be applied to a vector, and this vector is x or y. Okay. Oh, sorry, this doesn't make sense. Now it makes sense.
Yeah, that was my question.
Yeah. Okay. Okay. All good. So, and the last result, I'm going to compare all the results we are talking about in a moment, is the one of Uhabas and Achache. And this is from 2019. And they say, well, if your operator A, calligraphic A, now looked at a mapping from 0t to the bounded linear operators in L of v prime, if this guy is in homogeneous Sobolev space of power 1/2 from 0t with values in L of v prime. And actually, you only have to have this piecewise plus another condition. I will call this perturbation condition, but I don't want to go into details into this condition. Plus, you assume the uniform square root property. For A. So what is this uniform square root property? This says that your that your form domain is independent of T, and the operator realization of A in H admits a square root, which actually has this form domain as a domain of definition. And this for every T. And so I don't want to go into the details, but just say, just if you, in the particular case, of Osha and egot, this corresponds to, so this square root property corresponds to omega is Rn, or omega has Lipschitz boundary. So basically, you restrict the admitted sets on which you look into your PDE with this uniform square root property. Okay, and now I'm going to compare all these three. So we have three different results: Dia and Sascha, Osha and egot, and this Uhabas and arxiv. And the Dia and Sascha result and the Osha and egot result, so this one and this one. So you could think of, well, since there's a delta here and there's no delta there, you might think that this Osha egot result in the particular case of divergence form operators, which I will restrict my retention to in the following, should imply this one. However, since there's the supremum here, they don't really compare. So it really is the case that neither the one nor the other is sufficient for the other. Then you could think of, well, I know homogeneous Sobolev spaces, and I know that the homogeneous Sobolev space is, for H1/2, is characterized by this condition here. However, you can't have this, you won't have the supremum. But since you're also assuming this uniform square root property here, you cannot really compare this either. But if you look into this a bit closer, you can actually show that the Uhabas result is not implied by Osha and egot, but does imply it if you assume the uniform square root property as well. And the same thing, basically the same thing happens for the Dia and Sascha result. It is not stronger than the Uhabas arxiv, but if you assume the uniform square root property, then you get the result also for Dia and Sascha. Okay, and what is now the strategy of the proofs of all these results? And the strategy of the proof for Dia and Sascha and Osha and egot are commutator estimates. And in fact, which commutator is decisive here? The decisive commutator is actually the commutator with D1/2. So you look into, so if your form is something like divergence A of t gradient, then you look into commutators of the form of d1/2 A, and you try to control this somehow. And also the norm here is not common, so it's not the same norm for both the D and Sascha and the Osha egot. However, you look into this commutator things, and if you look into the Uhabas Achache situation, there it's not really commutator estimates, but rather a careful analysis of the variations of constants formula. Okay, and so whereas in the former two, the regularity comes into play because you want to control the commutator, and there is also where the 1/2 pops up. In the Uhabas paper, the 1/2 really pops up due to the square root property, and so because you're mixing these kind of things, so it's something, the perspective is changed in a way. And the aim of my talk now in the following, and basically of all this research with Sascha here, is really find a common strategy for all those three approaches, and try to provide a result of the form that if you have H1/2 homogeneous Sobolev regularity, then this implies maximal regularity. And because and this we do for divergence form problems only, and we won't, or we do not want to rely on the square root property, or which is the same in this situation here. We don't want to rely on boundary regularity. Okay. And in order to do this, draw a box around this. And in order to do this, I go now to step 1 and talk briefly about evolutionary equations. And this will be also the section where I introduce the main theorem of Sascha's and mine. Okay, what are evolutionary equations? Well, this is the standing point. So we want to understand a regularity result, but we don't want to use forms. So we try to use a different approach to solving partial differential equations, and this is due in its original form to Picard in 2009, and has been generalized ever since, in particular in 2013, which is a part of the theorem I'm presenting here. So let H be a Hilbert space, and we take a non-negative bounded self-adjoint operator in H, a skew self-adjoint, possibly unbounded operator in H, and a function from 0 to t with values in L of H, which should be bounded and measurable. And assume there exists a positive number nu and c such that for all t, we have that nu m0 plus real part of m of t is greater or equal than c in the sense of positive definiteness. This is now an equality of operator self-adjoint operators in Hilbert space. And if I assume this, then the operator sum dt m0 plus m1, and I'm abusing notation a little bit here, of multiplying by m1 of t. This is closable, and the inverse is a bounded linear operator in L2 from 0t with values in H. So this is also an operator sum, a similar sum we saw before. However, if we want to really look into PDEs, we need to reformulate this a little bit. So one example is the heat equation. And the heat equation consists of two equations. One is this balance law of dt theta plus divergence q equals right-hand side capital Q. And the second is Fourier's law, which is q equals minus and then coefficient kappa, possibly depending on t, gradient theta plus some boundary conditions. And if I look into these two equations, the evolutionary equation associated to this looks now as follows. So this is this 2x2 system of these two equations. So you have dt applied to theta, which is here, plus divergence q equals f. Sorry, this f is a q. And the second equation is q minus kappa of t gradient theta. So if I put this to the other side and multiply with kappa of t inverse, then I have the lower equation. And you see already that this guy is m0. This one here is m1 of t. And this guy is a. And the skew self-adjointness of A follows from the correct boundary conditions. So if you say assume directly homogeneous directly boundary conditions, then you have the boundary condition sitting on this gradient here, and this divergence is minus the negative of adjoint of this guy. So this whole block operator is skew self-adjoint. Or if you put the boundary condition on the divergence bit, then say this is then homogeneous Neumann boundary conditions, and this guy is the negative adjoint of this one. So you also have a skew self-adjoint operator A, and similar with other boundary conditions which you consider. Okay, and this M1 of t and this M0 of t, so this well-postedness or this positive definiteness condition here is then easily satisfied, because these two, this sum really separates into the positive definiteness of this guy and this one, and the former is, if you multiply this with the positive number, this is positive. And if you look into this kappa, and having assumed that kappa itself is strictly positive and bounded, then you will also have that this real part of kappa inverse is strictly positive. Okay, so this is the situation with the heat equation. And this abstract theorem I just presented to you, this is the correspondence. This corresponds to the well-postedness theorem leading to the Lyon's problem. And also in this case, one could then ask, well, if your right-hand side, which in this case is only our Q, is regular enough, does this if your right-hand side Q was an L2, does this then correspond to a regular solution theta that is in H1? And in order to really formulate this and to present Sascha's and mine result, we are considering a slightly more abstract situation than the one with the heat equation here. And this is the following. So we consider now problems of parabolic type. And this is if your M0 has the form of M0 tilde and 0, 0, 0 in a 2 by 2 block operator matrix. If your M1 has the form 0, 0, 0, M1 tilde of t, and your A has the form 0 minus C star C0 for some C from the domain of C in some Hilbert space H0 to H1. And your Hilbert space H is then H0 plus H1. And the main theorem is as follows. So the situation here I call PAR. So let M0, M1, and A be as in PAR. And if M0 tilde is self-adjoint and strictly positive, and the real part of M1 tilde of t is strictly positive. And a different condition here. If the real part of dt 1/2 m1 of phi dt 1/2 phi greater equal some constant c2, which is positive, and dt 1/2 phi dt 1/2 phi for all phi in h1/2. Then for all f in L2 of 0t with values in h0, we have that the solution uv to be really the sum of those operators again. So I take the evolutionary equation solution of this, then we get that u is in h1 of 0t with values in h0. And this is really the maximal regularity theorem, because if you compare this to the heat equation above there, and you take your q in L2, then the claim of this theorem is that your theta is in h1, and this is the same theta if you considered this equation here as second order equation in space, that you have maximal regularity. Okay, so this is the main theorem. I didn't say anything about what this dt 1/2 is here, and in which situation, in which setting you need to interpret this. But the message is that you can provide a functional calculus for your time derivative operator dt in a full time and in a Hilbert space, which considers the time axis to be the whole of R, and there you can actually compute this dt 1/2 and make sense of this condition. And in order to since I see that time is running, to wrap this up a bit, I close basically with the last part, applications. And this is as follows, because this condition here, this real part, this positive definiteness condition with involving this dt 1/2 is difficult to validate in practice unless you have some more conditions for your user. And so this condition here, I call this double star. So if, and this is, if the commutator of your operator dt 1/2 with m1 applied to phi in some L2 space is bounded by epsilon times dt 1/2 phi in an L2 space plus a constant c with phi in L2 for small epsilon greater than 0, then this star thing holds if you assume all the other conditions in this theorem. And this actually, this result here shows that that this implies Dir and Sascha. This also implies Osha and egot. And we are almost there to be able to that only the star thingy implies the Uhabas Achache condition. And so almost. And with this, I'd like to close and say thank you very much for your attention.
So, questions for Marcus?
Yeah, so your result is formulated in terms of these block operators, but obviously if you can apply it to these DZ and AE cases, it means that you can reformulate the problem, the parabolic problem, right, in this block operator form.
Yeah.
So basically it boils down to representing operator A in the form C M1 tilde minus C star, something like that.
Yes, so if you, so as I said, I'm only talking about divergence form problems here, really. So in the situation of the abstract form situation, you would have something like C star M1 of T inverse C. Sorry. I want to have a form here, so V and C W, something like this.
Well, the question is, so your framework, does it apply to the general problem with, as it was formulated by Lyons, with some more or less arbitrary operator A?
No, as I said, I'm focusing on divergence form problems only, and the only way. So the only way we know this the abstract form. Well, some form could correspond to the in the evolutionary equation setting is this situation here, and
yeah.
You could then, if you take C to be the gradient and C to be the gradient here, and this just be some matrix valued function, then also it's not clear whether in every situation you will get a square root from this. So you would need to have a regular boundary of omega to have the square root property, and
yeah.
And so this is our way to deal with the concrete problem, to avoid the square root property in hoping that just assuming the structure is sufficient to obtain this.
Yeah. Okay. Yeah, I see. Thank you.
Further questions, comments, remarks?
Yeah, one more thing I was wondering about is if you take this abstract result that you employ with these block operators and wrap it up as one equation rather than a system, would it be possible to translate this statement into this setting?
Yes, yes, definitely. The reason I'm presenting this in this block operator thing is there are more general equations you could look into with this block operator matrix thing. So you don't really need these zeros here don't really need to be there.
Yeah, I see. So it's in general, the statement of the theorem is for arbitrary, relatively more general class of operators, M1 and 0.
Yeah. But you could also this problem here, as I presented this, should in the second order situation looks more or less like this. So so it is dt m0 tilde plus c star m1 of t inverse c. This is your operator, and you apply this to u equals some f.
Yeah.
And the solution you will get from the abstract theorem with the block operators is a solution in the closure of this.
Yeah. Okay. Yeah. This is exactly what I'm talking about. If you take this abstract theorem in this specific case with the specific operators M0 and M1, can you reformulate the statement of this abstract theorem to this second order equation?
Yeah, so it's literally this. So here m tilde, right? So you only have m0 tilde, m1 tilde, c and c star involved, and the statement of the theorem is if m0 tilde and m1 tilde happen to satisfy suitable assumptions as these guys, then f in L2 implies u in H1 with values in H0.
Yeah, sure. Yeah. All right. Thanks.
No, okay, no worries.
Okay, if there are no further questions, maybe let's postpone further discussion to the informal coffee break. But before that, let's thank Marcus again for the nice talk.
Thank you.